Good evening. Tonight I'd like to go through a little bit of the hardware that we're working with, some things that we're working with now and things that we'll be working with in the future. Tonight I'd like to show you a little bit about the light optic fiber that we're working with. The large cable right here that you see is quite large, and I know the camera doesn't do a good job of showing this picture, but what's coming out of there right now is light from a laser. The laser is the little black box with the white sticker on top of it with the red and white pliers. That laser is being fed into this short section of very large tubing coming out, and the smaller tube over here is connected to a light array system that I'll be working on one of the future cells. With the advantages that we come up with the crystals and the pyramid, we're going to run light on both sides of the prism, and this is a demonstration of how it'll work. Pigtail will go out so that eventually there'll be eight of these units per cell with crystals, prisms on each side of it. I'm going to turn the unit on now, and if I can get it to work here. It has a remote control, it has a mind of its own. And this is not working. Well, wouldn't you know it with cameras. Oh well, we're going to come back to that in a second. What we'll look at right now is our power supplies that we're proud of. The one that you see right here comes from the manufacturer without a case or anything, and the display unit is separate here. It incorporates duty cycle frequency and memory lock for special frequencies that are set up. It's the unit that we're using right here that's on a fabricated metal box. The unit that we prefer right here is this one here. It's a constant current, and it's available both in a 30-40 amp arrangement as well as up to an 80. This unit is nice because it's very compact and has a cooling fan in it. The controls are set up so that they're not easily to monkey with the frequency and the limit on the current. This particular unit uses an analog meter for amperage to set it initially, and after that you can forget it. These units I like a lot. They're way good for smaller cells, but if you have a large output, or a large demand, this is the cell that you want, the power supply that you want. Reason being, in my opinion, it has a remote display for the amperage that goes through a USB cord right here, and the system has a heatsink right here, but primarily it's made for high amperage because the cables going into it are large battery cables. These you fabricate yourself, and there's one that goes into the system and the one that comes out. The manufacturer of this said that it did not need a cooling fan on it. He was wrong in my opinion, and we do have a cooling fan that cools this. It also has a control for the constant current, the amperage here, in the event that you did not need a remote cab display. Oh, and the next fun thing that we're getting into is this. You see these two things on top. These are called transducers. As transducers vibrate, and there's two of them on this particular unit that we have. These power cells have piezo magnets, which are the things in the center here separated by the metal. When these magnets are given electricity, they resonate at a certain frequency, and these are somewhat pre-programmed. It's hard to find ones that are adjustable. The power supply is behind it, This one was specifically made for the frequency that we believe is going to weaken the bond the best on the water molecule before the electrolyzer hits it, and this will be very interesting. The reason our test stand here was built with 2 round circles in it here and here was so that we would have the depth to put in these transducers. We'll be mounting 2 cells to this and then a transducer on each section. Some of the lighting that we've been introducing into the cell area has been with these optic cables here. I go back here and check this, and we got a flash out of there, so maybe we have a password. Alright, I don't think the camera's doing a very good job of it, but what we can do is change colors and intensities, as well as the frequency of the infrared remote sensors over here. It wasn't was hid from the fancy remote control. On the flashing right here, we can increase the speed of it to a very fast pitch. This particular one here is having some problems with the remote control, which isn't uncommon. Some of this quality Chinese hardware. Nonetheless, I think you get the idea. The little bit of light that is reflecting over here on this piece right here, I'll kind of turn that in so that some of the light is facing into that. We can see over here right away. So the fiber optics is very effective. It works very well. So using prisms and light and frequency, using photoelectric theory, and then going into what's called molecular vibration. And water has a frequency. It's 427 kilohertz, 427.7, I believe, something like that. We have 4 of these boxes that hold 4 different frequencies that we feel will be the key to getting some good results. I'd like to go through the PEM operation with you, but I think we'll save that for another time. And I appreciate your time of looking at what you have seen, and thank you for watching the video. What we're looking at right now is the front of the high pressure electrolyzer. We're running around 36 amperage input, and the cell temperature we can see is 70 degrees. Water level is in the middle of the scale, and we're fine. We're building up gas right now. Our gas gauge is rising right there, and we're going to be administering some gas with, if I can find the camera, this torch tip. Has the cover off it right now. It's 2 cylinders that are of sleeve valve design, with a connection in the bottom carrying the current, or excuse me, the water flow, and they're connected together with a hose to numerous safety protocols and valves, both electronic and mechanical. Good evening. Today we're going to talk a little bit about pressurizing HHO. What we have in front of us is a round black tube that has a hose coming out of one end going to a simple on-off valve. The valve, the tube is sealed on the other end. What we're going to do with the tube is put HHO into it. We're not too worried about pressurizing it. I won't get started about that now. And what you see here is a vacuum pump, typically used in automotive repair shops, which I own, to evacuate air conditioning systems. It's capable of putting a 30-inch minus vacuum, which will measure on these gauges right here, so that when we do pressurize this cylinder, it'll be under a vacuum and have no oxygen in it, as well as be more acceptable of taking in the charge. Where the gas is going to come from that we're going to insert into this tube is from this 2.5 gallon baggie that I've been filling up and using for health treatments. This bag is going to be fed into this little gadget, which is a converted pump from a tire pump. And after some serious messing around and machine work, we got to work very well. And we'll feed this pump the gas. This will pressurize this cylinder, and when I go to do a treatment, I won't have to carry a baggie around, but rather a tube with hydrogen. Now, certainly the valve and the plumbing is less than what I'd like for something permanent, but for test purposes, it's proved very adequate. The pressures that I'm running in it are no more than 50 psi. What we're looking at right now is 2 transducers and a power supply. These are what is going to vibrate the water on the next video. There's about 18 of them located underneath a container of water, and when it's turned on, you're going to see some extreme agitation. These will help destabilize the molecule, as well as help remove the bubbles from the plate. We've been experimenting with different frequencies and having great success with it. Wanted to let you know what's going on because the next video is quite interesting. Thank you for watching. What we're looking at is the pressure gauge on the electrolyzer. I'll squeeze the line shut now. We can see how quickly pressure rises. Here's some hissing. We've got a leak. As you can see, hitting 4 psi didn't take very long. Good afternoon. We're back again with a project that I wanted to mention and get on film. It's a cook stove that we're working on. The cook stove will operate from HHO as a fuel. Plasma. Because I'm using a battery charger, the top waveform, yellow one, is what got a lot of interference with it. If I turn the battery charger off, you can see how straight it goes. What we're looking at now is, on the yellow pattern, is a square waveform of the current going to the electrolyzer. And the frequency of it is down here in the blue area. We can see it's around 500. It's oscillating a little bit. And it should be very close to this reading here
which is the controller instrumentation at 488 hertz, and we're at 95 on the duty cycle. Now I'm going to turn the duty cycle down a little bit, and you're going to watch the pattern change as the current is reduced on its time and it's on. Now we've got it at 100% duty cycle now, so the PWM effect is non-existent. We're having a straight solid current going to the cell right now. It's not being pulsated. It couldn't at 100%. At 92, we start getting the effect of the modulation of the voltage, and we can see that how the pattern changes as the current is turned up and down. These are divisions in milliseconds, and we've got the screen in the large display mode. As I turn the frequency up, you'll see these patterns bunch up together. As the frequency gets higher, we're up to around 3,000 on this. I see it hitting, which is really the maximum frequency on this controller. And then we can separate the frequency, and we can see that they're spaced out more. The pattern on the bottom is the pattern for the light array that's red right here. And this has a pulse width modulation square wave. And you can see that as I increase the length of the pattern on the top, the array gets brighter, and then reduce it down. This one right here, we'll go over to this channel, and our frequency is set at 700 on this particular controller. When we get the transducer patterns on here, we'll have 3 patterns. And to control certain items, we're able to use a feature called the signal generator. And the signal generator is very unique in that it allows us to do a PWM signal with any frequency that we want, with a duty cycle, or we can go down to basic waveforms here and control frequency as well as which type of pattern we want displayed on. Our amplitude and offset are fully adjustable, and as we use this type of tool, we can record everything into the memory of the computer and play it back. On the bottom of the PC, you see this is the main oscilloscope ECM. This on the side right here is the signal generator, and it's over here, and this signal generator commonly runs a TTL board, which is this circuit board here, and it stands for transistor logic. It's much like a relay in that when it gets a signal, it'll cut off the display of the laser. We're at 20 hertz right now, and if you look at the laser, you can see that it's blinking. If we were to go up to 25 or 30 cycles per second, the beam would turn into a solid beam of light, as your eyes would not be able to distinguish the differences. Signal generator, fantastic item, and then it gets into something that is quite unique. It's called a logic analyzer, and it's this second module that plugs in, It has little connectors that allow you to connect directly onto an IC chip, and it helps you coordinate signals and look at logic in the chips themselves. What I'm using it for is to help me signal and synchronize signals so that we can weaken the bond before the electrolyzer hits it. On the screen right here, you'll see different colors, and they correspond with the different lead colors that you see on the harness. And the patterns are displayed crossways through here. And when we show the units with the transducers on them, we'll definitely go through a full display of this right now. But right now we'll go back to the oscilloscope and we're looking at our patterns here. Now what we can do is go to what's called the control window. And on the control window here, we are able to display the pattern in different time increments. We can go as high as 500 milliseconds or as low as some very low readings. Right now we're at 1 millisecond divisions. The blue scale right here is on a 2-volt scale. We're on a times 10, so it'd actually be a 20-volt scale. The one on the yellow down here is on the half-volt scale, which is this one here. We'll go over here and we'll change it to 2 milliseconds, and you can see a little bit difference in the pattern. We'll go down here to 5 milliseconds, and you can see how much closer the pattern has become together. It's a preference of the user how he likes the pattern displayed. This can all be recorded and played back and sent over the wire. All right, with this and the ability to control the signals and use the various aids before the electrolyzer hits it, I think we're going to have some good readings. All right, thank you.
What we're looking at right now is what's called a reversible PEM. PEM stands for reversible, my mind's going blank, proton exchange membrane. This is a reversible PEM, and what that means is it creates the gas and then it uses the gas to turn it back into electricity. Now what we're going to do here is apply voltage to it with these batteries. One side here that says O2, we'll put O2 through this hose into the yellow chamber, which will rise because there's water inside the green container. The other one is hydrogen on this side, and it's on the other side of the unit where the black wire is going, and it has a hose that's connected there. It wasn't working very well till I realized the batteries were dead that I was using. What this technology allows us to do is, say we have a solar or we have wind generation. In the daytime, a machine like this could make the gas, store it, and then turn it back into electricity at nighttime. Imagine if these were large garbage cans, a 50-gallon can with a smaller one inserted with some hoses going into it. With the water in there, the flame would have to go through the water and up into the chamber. And one side would be oxygen and the other side hydrogen. Hydrogen needs oxygen to burn, so it's very hard for it to be dangerous. Now, when I connect the battery up to this, you're going to see movement in this hose right here because there is still some moisture in there. It's a little bit overfilled. Now this one here carries the hydrogen, and it's going to go up twice as far as the one with the oxygen because we're getting a 2-to-1 breakdown. Now I'm going to connect this over here with my hand to, excuse me for the camera for a second while I do this. Okay, it sure does take a long time when you're trying to hurry. Okay, we can see the hose and the fluid moving through it very rapidly now. The water's been pushed out, and you can see the container is rising quite rapidly along with this one right here. Now that is pure electricity what we're storing, and you can see how fast that it rises. It's amazing. Okay, that didn't take very long, obviously. Now what we're going to do is take these same wires and we're going to connect them to this light, and we will see electricity that will come from gas. The unit basically consists of 2 pieces of stainless steel mesh with a membrane separating them. The membrane is made by DuPont, Nation, something like that it's called. This particular unit came from Germany years ago, and I had a little trouble getting it into the United States. The proof of concept is proven here. Not that this is going to be any great power source, but they're in different sizes. And it shows you that gas can be turned into electricity with no electric motor running and no noise. And above all, it's very efficient. I'm going to stop the film now and come back when I've hooked the 2 wires up and won't put you through with my fumbling. Alright, we'll be seeing the next video next. Thank you for watching so far. Well, we're back, and we definitely have some gas produced. The positive wire I've wrapped around there. And I've got an alligator clip here that I'm going to connect to the back of the light bulb here to give it a ground. Okay, you can see the light's very bright. We'll turn this away, and you can see we have quite a strong light. And if we look down here at the cylinder, they're not dropping very fast. It takes a long time. The light stays on far longer than the time it takes to make the gas. Probably double. Now, this is a 6-volt light bulb, and you can certainly see how bright it is. These things could be put in series, and 3 of them I've taken camping with a cylinder of hydrogen and had electricity for the whole weekend. As you can see, the light stays on, the cylinders don't seem to move, and that little jewel is putting out electricity. And you can see the dark spots there. That's the water that's in there that it's used in the beginning when it was making the hydrogen. And you should keep some in there to keep the membrane moist. Proton exchange membrane. I hope you enjoyed it as much as I did the first time that I played with it. Very quiet, the way that I would want my generator to run. And you can see it takes very little gas. Alright, this is the last video that I'll be making, and we'll have 4 videos that'll be sent out, and I hope that you look at all of them and give me your comments back. We're planning on making many videos. We discover new things every day, and we just have to put a stopping point so that we can show where we're at so far. The videos that you will see are the result of about 2.5 years of work. Alright, thank you for watching it, and good night. Oh, it's about 12 a.m. in the morning, and I just couldn't help but get this on video. It's the first time I've got the light technology working from a signal generator that's keeping a special signal and coordinated with 2 other signals, and boy, did I get an improvement. The temperature is much lower, the output's higher than I've ever had it, and we're still under 10 amps. I'm gonna sleep better tonight. Thank you for watching.